Today we're going to be talking about integrated rate laws. Integrated rate laws are where the concentration will depend on time in your graph. So you could see that in the first graph we see concentration and time, and you see you have a straight line. This would be a zero order reaction. So there are three possibilities that we could have. We could have a zero order, a first order, or a second order. Zero order, first order, second order. They're all going to be concentration versus time. And what you'll find is that a zero order will automatically come out to be a line like this. However, if you graphed a first or second order reaction, you would have a curve. One would look like this. The second one would be a little more steep, but you would never be able to know that just by looking at the graphs, because the scales could easily make either one of these look like the other. So what you want to do is to understand a first order versus a second order, you want to be able to turn these curves into lines. So you would do different mathematical things to concentration and regraph. For instance, you could do the concentration squared, or you could do the natural log of concentration, or you could do 1 over concentration. And by experimenting with those numbers, you would find how to make a linear graph. So what you will find is that with a zero order, it will come out to be a line with concentration. However, with first order, it would result in a line only if you change concentration to ln of concentration versus time. And for a second order, you would find that it's 1 over A versus concentration that gives you a straight line. Now with these straight lines, the slope of the line is going to be equal to K, which is the rate constant. So the slope is actually equal to negative K because K is always positive. The K that we learned about when we said rate equals K times concentration of A, in this case to the 0, this rate constant is the same rate constant as this. Since K is always positive, therefore the slope of this graph is the negative of K. Now in a first order, again, the regular rate law, the differential rate law would be rate equals K times concentration of A to the first. And this slope right here is going to be the negative of K as well. And lastly, for a second order, you would find out that the slope is simply K, positive K, because it already is a positive slope, and this differential rate law would be concentration A squared for a second order. Let's talk about our intercepts for each of these graphs. Since we're simply plotting concentration on a zero order, the intercept is going to be the concentration of A at time 0, the initial concentration. Versus here, the intercept is going to be the ln of the initial concentration of A. And the intercept of a second order is going to be 1 over the initial concentration of A. So these graphs are lines. And a line is always a y equals ax plus b. So what's my equation for the line here? It's y, which is concentration, which is right here, equals the slope, which is negative K from the graph, times the x, which is time, plus the intercept, which is the initial concentration. If we contrast that over here with the first order, you're going to find that first order, the y, is the ln of A, which is right here, equals the slope, which is negative K, times the x, which is going to be time, and added to the intercept, which is the ln of A0. And lastly, you could follow with the second order, it's the same thing. The y is going to be 1 over A, the slope is positive K, the x is time, and the intercept is 1 over A0. And this is where you're getting all these highlighted equations of the line. Now each of these also has what's called a half-life. A half-life is the time it takes for half of the substance to react. So the half-life equation for zero order is A0 over 2K. For first order, it's 0.693 over K. And for second order, it's 1 over Ka0. Those are the half-life equations. So these are the general mathematical equations we need to understand for integrated rate laws. And then what we're going to do is use some data in the next slide to figure out which order a reaction is. We're now on page 6 of the AP Chemistry Chapter 12 packet on kinetics, and we are going to be using some data below right here in order to figure out what order this reaction is. Is it first order, second order, or zero order with respect only to the NO2? That's the one we're going to figure out. So remember that if we graph concentration versus time and we find a straight line, already we know that's zero order. If we graph concentration versus time and we get a curve, then we know that it's either going to be first or second order. So now the question is, well, how do we figure out if it's first or second, which one it is? Then we have to make a second graph and find out, does the ln of concentration versus time come out to be a straight line like this, or does 1 over concentration of A versus time come out to be a straight line like that? And if whichever one is the straight line is going to tell us which order it is. Okay, so what we're going to do is we're going to use our graphing calculators, and you need to pull yours out right now if you don't have it, and you need to make time your list 1 and the concentration of NO2 your list 2. This is your list 1, this is your list 2. So you can pause the video, put that in your calculator, and then after you're done, we'll unpause, and now you're going to see that this graph comes out to be a curve. So since this comes out to be a curve, you know that this is not zero order. So it's not zero order. So it's either first or second. So now what we're going to do is we're going to try the ln of concentration versus time. So if this is your list 1, which is time, and this is your list 2, which is concentration, you're going to make a list 3, which is going to be the ln of concentration, which is list 2. So make a third column, a third list, make it the ln of concentration, and then plot that on your graphing calculator. And you're going to find out that that plot comes out to be a little bit curvy, not very straight. It's kind of like this, a little bit. So you're going to double check that with your last one, and you're going to find out if 1 over, I should have written NO2. We're dealing with NO2 here. So the ln of NO2 was not quite straight. Go ahead and try 1 over list 2 for your list 4. So let's write that in here. This is going to be 1 over list 2. So make a graph of list 4, which is going to be 1 over list 2, versus list 1. And you're going to find out that this does come out to be a good straight line. Now, how could you, besides eyeballing it, how do you know it's a good straight line? What you want to do is you want to go to catalog, which is the second function of 0. And under catalog, you want to go to diagnostics on. Oops. Diagnostics on. And when you turn diagnostics on, it's going to tell you what the correlation factor is, okay? The correlation factor is R. If R equals 1.000, that is definitely a straight line. The closer to 1 it is, the better. So if you were to look at the R value of your first graph, even though it's 0.9 something, it's not close to 1 really. The second graph has a better correlation factor, but the third graph has a really good one. It's like 0.999 whatever. So the third graph is the straightest line. So diagnostics is going to tell you with your R factor or R squared, either one, you know, just be consistent whenever you're looking at these. Either R or R squared needs to equal 1.00. Okay, so now that we figured out that it's second order, we're going to write our answer here, that this is second order because 1 over concentration of NO2 versus time was a straight line, because you already tried the regular concentration and you already tried ln, so it was not 0 or first order. Now we're going to go to the second one. Let's find the value in the units of k. Well, this is where you're going to use your graphing calculator. The slope of this graph is k, positive k. So look at your calculator, and you have to go to stat calc, and you're going to do list 1, list 4, because list 4 was the straight line, and you should have found out that your a value was 2.10 times 10 to the minus 4th, and your b value was 2.01 from the graphing calculator. So that means that the k is the slope, and slope is a. So the slope is 2.10 times 10 to the minus 4th. And now you need your units. Remember our little trick? We turn over liters and moles from moles per liter, and we raise it to 1 less than the total exponent. So since we found out that this is second order, 1 less than that is 1, so we raise each of these to the first. We put our time unit on the bottom. Our time was in seconds, so this is going to be liters over moles seconds. Now be careful, because another way to write this is molarity to the -1 times seconds to the -1. Okay, that's the same exact thing. It could have been a 1 over molarity and seconds on the bottom. Okay, so any combination of these is going to be okay. You just got to be careful with the units. Next, we want to find the missing values. Whenever you're looking for a missing value, you're going to use your y equals ax plus b equation for the line. So remember, the line is 1 over concentration equals the slope, which was 2.1 times 10 to the minus 4th times the time, all right, plus the intercept. So the intercept was 2.01, and let's say that we're dealing with this missing time right here. So if we're missing with that missing time, that's going to be my x, and then the concentration is going to be 0.422. And when you do all the math for that, you should get 1700 as your answer. And 1700 makes sense because 1700 fits right about here between 1200 and 3000, and 0.422 fits right there as we're decreasing from 0.444 to 0.381. Okay, now we're going to try to find this missing blank. So we're going to use the 12,000 as our time. So we're going to do that over here. So 12,000 is now our time. We still have the same slope, of course. We still have the same intercept. And now we're going to solve for 1 over x. X is the missing concentration. When you do all that math, I don't have it written down, so we'll have to do it real quick. We're going to take 2.1 times 10 to the minus 4th. Just got to get out of this. Kind of pause. So the answer to this was 0.221. And 0.221 makes sense because 0.221 fits right over here, and 12,000 seconds also fits right over here. So it makes sense that at 12,000 seconds we'd have 0.221 concentration. Okay, the last thing we need to do is to find the half-lives. So what you're going to use is the half-life equations for these. And half-life equation is going to be, first half-life is going to be 1 over Ka0. Continuing on, we're going to find the half-life of the equation. And to do that, we're going to use the half-life formula that T1 half equals 1 over K times initial concentration. This is from the notes for a second order. This is the equation. So the first half-life is going to be the time it takes for half of the reactant to react. That's the first half-life. So what is the K? We just found is 2.10 times 10 to the minus fourth. And we're going to multiply that by the initial concentration, which was 0.500, and that's going to be in the denominator, and that's going to come out to be 9,500 seconds. That's the first half-life. Now this actually makes a lot of sense, because if you look back at the data, you will see that the amount of 0.5 went down to 0.25 in 9,000 seconds, which within sig figs is close enough to 9,500. So that makes sense. Now the next question is, how long is the second half-life? That means it's going to go from 0.25 to 0.125, which is going to be somewhere over here. It's going to go to 0.125. So we're going to find out how long it takes to go there. So to do that, we're going to use the half-life equation again. But this time, sorry, some of these numbers are not moving. It's just strange. So the second half-life is going to be T1 half is going to equal 1 over K A0. Now you have to be careful with this A0. If it's the second half-life, that means it already had the first half-life. So we still have the same K, which is 2.10 times 10 to the negative fourth. However, the new initial amount is not 0.5, but it's 0.25 because it already cut in half once. So that's the new one. And now we see that the next half-life is 19,000 seconds. That's 19,000 seconds on top of the already 9,500 seconds. So this is 19,000 seconds after the 9,500 seconds that we already had. Okay, lastly, we're going to find out the percent remaining after 4,000 seconds. So again, whenever you need to know how much is left after a certain amount of time, you're always going to use the integrated rate law, which is the y equals ax plus b. So the y is 1 over an amount of NO2. A is the slope, which is 2.10 times 10 to the minus fourth. The time is 4,000 seconds. And again, the initial amount is 0.5. So you could write 1 over 0.5, or you could use the intercept that the calculator gave you. Within sig figs, it'll be the same thing. And then when you do all that, you're going to get 0.352. So the concentration of NO2 equals 0.352 molar. Now that's how much is remaining, okay, but you want a percent. So if that's remaining, how much did you start? You started with 0.5. So let's change colors here. So you're going to take your 0.352 remaining out of the original 0.500 times 100, and that means that you have 71% remaining. Now a trick question would be how much reacted, so that would mean 29% reacted. And that's how you would figure out an amount after a certain amount of time. You always are going to use the integrated rate law to find out how much is left after a certain amount of time.